So hello everyone and welcome to this new course that we are starting from today, and it is a it is an online course on design and detailing of steel structures using AISC codes. So first of all, we would like to thank you for joining this course, and I hope we will have a good time uh, learning the steel structure design using AISC codes. So many of you are participants who have taken courses with us before. So thanks to all of you for your continued participation. And many of you are also joining the Oxygen course for the first time. So I can assure you that we will have a good time in this course, learning this together. A few things before I start, that all of you will be on mute during the duration of the session, and your videos will also be switched off. So that means you will not be able to switch on your videos or unmute yourself. So if you want to communicate with us, you can just type in your query in the chat box. And during the session, we continuously monitor the chat box. So whatever you ask, uh, we will be reading it, or whatever you want to say or comment or anything you want to communicate, you can just put it in the chat box. Uh, we are constantly monitoring it, and we will reply it if it's a question or take note of if it's a comment. Okay. So I hope my voice is audible and you can see me and listen to me. You can also are able to see the screen where I am showing you the first session slide. Is it visible? Hello. Just type in the comments. Yes, no. I hope you are able to use the chat box. Let me just see if, yeah, you're allowed to use the chat box. So just put in some hi or hello or whatever so that I understand you are able to see all these things. Okay, yes. Let's begin then. So quickly, uh, showing you a PPT for the first time and for the last time during this course. Uh, but let's see what we have. So just a few things which I would like to repeat from what was already discussed in the introductory session. And then we'll also just have a quick look at the details of the course. And then we will move on to the historical development of the steel specification of structural steel code that we now know as AIC 360. We'll just have a look at the historical development of this code over the past 100 years. And then we will also look at the historical development of the seismic provision that is now known as AIC 341. So let's start our discussion then. Okay. So why to learn steel design? I think we have already seen this, that in spite of the importance of steel structure in the infrastructural projects and industrial projects, and these days more so in commercial and residential space, in spite of its increased or in spite of its prevalent use, many structural engineers often find difficulty in structural steel design. And then it is more so because that subject does not get taught properly at the engineering or at the postgraduate level. And the books and documents available focus more on the theoretical aspects, but they don't teach the or they don't discuss the actual design aspects. And because many of the structural engineering firms also are involved more in the RCC design, so many times the structural engineer is not even able to learn structural steel design on the job because their office is doing projects mainly in RCC. This also happens that in bigger companies there are different departments for steel design and RCC design. I don't know if you where you are working, if the participants who are working professionals in their company, is there a different department for steel design and RCC design? Because where I used to work, there was a different department for steel design and RCC design. So the people who were involved in steel design, they used to only do steel design. So they would not give the steel design work to the RCC department. So in bigger companies, this type of segregation may happen. So what I'm trying to say that because many of the companies are also involved in RCC design or RCC projects, the structural engineer is not able to learn steel design on the job. And that's why these days the trend has increased that because the engineers find themselves not capable enough or not confident enough of doing steel design, they often outsource their work and then they rely on some pre-engineered steel construction companies who will do the design and who will do the fabrication, erection, everything. So just like there are the PT companies these days for RCC, many of the RCC elements who will do your PT design for slabs or beams, etc. So the structural engineer is not aware of PT design, how to do the PT design of RCC structures. So they will rely on some company who will do the PT design and who will also do the installation work for them. Okay, so that skill has been outsourced, so to say. The same thing happens in steel companies also. Anyway, we all know this. So now why to learn steel design using AISC code? Again, it's a repeat slide which I had already shown you before, but let's just have a look at it again. That the steel design codes by AISC are one of the most up-to-date codes available to the structural engineers across the world, and they have been getting continuously revised. And I'll show you in upcoming slides that how since 1923 when they were first launched, they are getting continuously revised since then. Okay, so in these 102 years, there have been regular revisions, and whatever is the latest in terms of material or in terms of uh, behavior of steel sections or in terms of research that has been carried out or in terms of, let's say, the experiences of engineers, all those things are regularly included in the code and then they are updated quite frequently. So AISC steel design codes are one of the most up-to-date codes, and they are also widely used in and they are of course one of the most widely used design standards. So which countries use AISC code for their design? So I think in the Indian subcontinent, I guess Pakistan, Bangladesh both use the AISC codes. Just add to this list. As far as I know, Pakistan, Bangladesh in the Indian subcontinent. Then you have got the Middle Eastern countries or the Gulf countries. Almost all the Gulf countries are using AISC codes for steel design, or so to say, American codes for their design work. They are also using the ASE standards for loading. They are using the AISC codes for steel design, ACI codes for concrete. So, and those who are not using directly, what they do, just a minute. Are you able to see the screen? Tell me what is visible right now on the screen. Screen is visible, right? Okay, yeah, yeah. So I was telling you that the countries in the Indian subcontinent, just a minute. There is some change in this Zoom interface. So I'm just trying to figure out. Ah, so I guess, and what I'm writing on the screen, is it visible? So all the Gulf countries like Oman, Bahrain, Saudi, Qatar are using codes. UAE, all the Emirates, all the Gulf countries. Then you have got, I guess, the South American countries, the Latin American countries. Many of the South American countries are using the AISC codes. Then you have got the Southeast Asian countries are using the AISC codes. So many of the countries are using these AISC standards, and if they are not directly using, what happens? That their country codes are based on them. For example, many of these Gulf countries that I just named, they have some sort of building manual or building code, and where they will say that steel design has to be done as per AISC or concrete design has to be done as per ACI, like that. Understood? So even though their code may not be directly based on AISC, but then they will have, sorry, even though they may not be referring directly to AISC, but then they will have their country codes based on them. So this AISC 360, which is the basic specification for steel structural buildings, or it is the parent code, just like IS 800 2007. This is a comprehensive document and with commentary, with quite a detailed commentary, which Indian standards have not been able to manage till now. So I think the IS 456 only has a commentary. IS 456 had a commentary, and that too the IS 456 of 1978. I guess that had a commentary which was published in 1980, which was named as SP24, isn't it? So SP24 is the explanatory to IS 456 2000. Sorry, what I'm saying, not 2078. So IS 456, when it was published in 1978, it got a commentary or explanatory handbook in the form of SP24 that was published in 1980. Since then, I don't know of any code which has had a commentary or explanatory handbook for it. Is there any code which you can recall which has an explanatory handbook? Hello. And no such explanatory handbook was published for IS 456 2000. So after 78, when the next revision came, there was no handbook or explanatory or commentary published. So no Indian codes usually have any commentary with them. So the structural engineers or the practicing engineers have to figure out for themselves what's happening in the code. But the Bureau of Indian Standards does not publish any commentary or explanatory handbooks. But then these American codes have good commentaries, good explanatory documents published with the code itself. So it does not happen that the explanatory will come 3 years, 4 years after the code. No, it comes with the code. Anyway, so it's quite a comprehensive document. And what I have come to understand from the study that I have done for these AISC standards, that you may be using IS codes for your design, but if you understand or if you go through AISC 360 also, you will get to know a lot of things about the behavioral aspects of steel structures. You will get to understand a lot of design concepts and limit states, which will be useful for you, just not while using the AISC code, but other codes also. For example, you are using IS 800, you are not using AISC, but if you study the AISC 360, you will begin to appreciate what is given in the IS 800 also, and what is the pluses and minuses of this 800. What are the things that have been addressed in AISC 360 that are missing in IS 800, and what are the few things that are there in the IS 800 but not included in AISC. Then you will be able to compare different country codes. Okay. So if you are able to understand AISC 360, which is the most comprehensive document, in my opinion, if you are able to understand this code properly, then I think you will be able to use other country codes also very easily for design work. Is this clear? Hello? Quick yes, no? Okay. My voice is audible, right? And then, as structural engineers, it's also important for us to understand the ductile design and detailing based on these two standards, AISC 341 and AISC 358. I'll be talking more about this later in the session today. And then not only understanding the code, but then we also need to understand use of software like ETABS+, STAAD+, etc. So in this course, we will be addressing all these issues. And this course, I think no need to repeat it. What we are going to do, so these are the topics that we are going to cover. Today we'll be focusing on this historical development. So these are the list of things that we'll be discussing in this course. This gravity load calculation and wind load, seismic load calculations, uh, we will slightly shift it to the later part of the course when we start the sample project. Okay, so when we start the sample project, and because at that time we will require the gravity load calculation and wind and seismic load calculation, then we will look at the we will look at the relevant ASCE 7 provisions for those calculations. All right. And then we will, so these are the list of topics: discussion on material grades, configuration, this analysis requirements. So yesterday someone was asking that will you be discussing the direct analysis method? So in the in the AISC 360, there is this direct analysis method, uh, which talks about the stiffness modification, which talks about including the secondary effects, which talks about including the notional loads. So all that comes under the direct analysis. So we'll be seeing this also. And it's quite interesting if you read the commentary for direct analysis given in the AISC 360. It's quite interesting, and you will get to know a lot of things which are, I think, missing in IS 800. So IS 800 also has this concept of notional loads, but then that portion is not very well covered in the code. If you refer to section 4 point something, 4.3 point something, there is this concept of notional loads given in IS 800 2007 also. But then it's not very well explained. And as a user, we are not able to understand what actually to do. But then if you read the direct analysis method given in AISC 360, it's quite comprehensive and informative. And we get to know a lot of things about the direct analysis method and how to perform it in the software. So this we will focus when I say the analysis requirements. We'll focus a lot on it. It is covered under the section C or chapter C of AISC 360, the analysis methods. And then we will look for the members and design the members for design actions, various design actions. And then connections, of course. First members, then connections. I have not understood till now that why in the books, and I have discussed this before also, that why in the books on structural steel design, they cover the connections first and then they cover the member design. I don't know why it happens in the books. Have you seen this in the steel design books that Connection design comes first, and then the member design comes. Since my college days, I have never understood this, why this happens. In fact, that leaves the user more confused because the user first learns the bolted and welded connections, and then the user or the engineer gets to learn the member design if he or she is reading from books. So it really gets quite confusing uh, as to why the books on structural steel design are made in this manner. I've never understood this. But then we will not do it this way. We will first study the member design and then we will study the connection design. Okay. So yeah, so welded and bolted connections, how to do the proportioning, etc. Design the detailing for different connections, beam column shear, moment connections. All these things I have already told you before, so I'm not repeating it. And then we will go to the ductile design and detailing of steel structures, the member and connection requirement for ductile design and detailing, the system requirements for a few systems, and then specific requirements for connection design, and then interesting use of pre-qualified connections for IMRF and SMRF. This is what is covered in AISC 358. And then in the end, we will take two sample projects. And as I told you before also, we will focus more on these two types of sections, which are the three plate sections. These can be rolled, hot rolled, or fabricated. That means made out of three plates by joining three plates together, three distinct plates welded together. We will call them as fabricated eye sections or three plate eye sections or your rolled eye sections. Now, why are they used more? Can anyone tell me? Why is the use of eye sections more prevalent? Yes, please. Any comments from anyone? We would like to have comments flowing in the chat box so that we can make the session more interactive. Yes. My question is, why do you see use of eye sections more prevalent? More prevalent means why are they used more commonly in the steel section design? Mr. Nagesh is saying they are easy to fabricate. Yes. So you can say, first of all, see, rolled sections will have some limitation. All of us know that they will have standard sizes. So if you talk in terms of the ISMBs, Indian standard sections, the largest ISMB you get is ISMB 600. You cannot get more than that. And in the rolled sections, the section dimensions are such that they are quite stocky sections. And for many of the uses, you are not able to achieve economy if you are using rolled sections. They may be very good against the effects of earthquake, but they are not uh, optimized for your general locations where you don't expect earthquakes to strike quite often. So rolled sections may not be the best and most optimum sections that are available, hot rolled. So therefore, to achieve economy, people try to go for built up eye sections where they will have three plates joined together. So in the earlier times, what used to happen that you would use angles. In the books, you will quite often see these angles, and then those angles were used for connecting these plates. Yes or no? Hello. So through bolting or riveting, riveting is now finished. It is obsolete. No one does riveting now, but still books do riveting. Anyway, so what used to happen in the earlier times, the three plate sections, they would be joined together by use of cleats. So for example, these are my three plates. I'm just drawing 3 plates in 3 different colors. I hope you're able to see it. And then there will be this cleat. So you would have angle. I'm sure we must have done this type of section in our graduate study. And then there would be riveting or bolting over here. Yes or no? So this was what was done in the earlier times. But now with the advancement of welding techniques, with the improvements in the welding technology that we have, so now we don't need to rely just on the uh, electric arc welding. We can now have the inert gas weldings or the shielded gas welding techniques now. We have welding lines now where the member can say stay in one place and your welding equipment will move. So there are very good welding technology that is now available. And because of that, without use of any cleat, just by welding over here, we are able to achieve very good strength eye sections. Is it clear? Hello. So eye sections are easy to fabricate, easy to fabricate, and what else? And they, what should I say? They offer the structural designer great flexibility. Flexibility in terms of the sizes that the structural designer wants to choose. Offer structural designer great flexibility in design. Is it clear, please? Flexibility means not that flexible, stiff wala flexibility. Flexibility means it offers great options to the structural designer in choosing and optimizing. So depending on the usage, depending on what you are going to use that particular member for, you can accordingly proportion the flange widths, flange thicknesses. You can accordingly proportion the web thicknesses. You can accordingly proportional the web depths. And then to avoid local issues, local failures, we are also we also have that option to add stiffeners. So we can add transverse stiffeners, longitudinal stiffeners if required. Okay. So in this manner, we are able to optimize our section a lot. Is that clear? So that is one of the reasons why these 3 plate sections are uh, used a lot these days. Another reason is that to further achieve economy, you are able to you are able to make tapered sections. Do we understand tapered sections? Hello? No? Tapered section means this is, I am showing you the elevational view. So what we are doing is that something like this. So what's happening over here? This is my flange. This is my flange. And this is my web. And what you see that in the web, I am making the web plate in such a way that this is the elevational view. So I am making the web depth in such a way that I am able to reduce the section moment of inertia at different sections. So if I were to see this sectional view, let's say AA, how would it look like? So it would look something like this, where I have my voice is audible. Hello. So this is the section at, let's say, AA, and this is the depth. that I get at this H2. This is what I get at section AA. And then at section BB, what's it that I'm getting? What is it that I get at section BB? So at section BB, I get this. So what are these called as? These are called as web tapered sections. If you refer the AISC, usually they will call it as the web tapered sections. Why web tapered? Because the web depth is being varied along the length of this member. Is that clear? So with plates, you have this option of fabricating the web tapered sections also. And if you see the industrial or pre-engineered, prefabricated buildings to further optimize your steel quantity, you will see a lot of these web tapered sections. And then there is this AISC design guide number 25. We will have a look at that later. But then there is this AISC design guide number 25, which covers the web tapered sections. Clear? So design guides are something like a small document of 15-20 pages, which focuses on a particular topic, and then uh, it gives the designer or the structural engineer some tips and some basic theory on a particular topic. So there are, I think, 40 such design guides. I think most of them are available to be downloaded from the internet through some websites like Scribd or academia.edu or PDF Coffee. From these websites, many of these design guides you can easily download. So AIST design guide number 25 covers the design for web tapered sections. So what I'm trying to tell you that three plate I sections or three plate sections are very uh, popular and one of the most commonly used steel sections. So we'll also focus more on them. And similarly, hollow sections are one of the other commonly used popular sections. So we'll try to focus on them also. Now, can someone tell me why hollow sections are popular, or why are they more commonly, why are they also used a lot? Hello. I sections I tried to explain. Hollow sections, why are they quite popular and used a lot? Tell me. So hollow sections offers you great efficiency of shape, and for the least material, you can say you get the most optimum, most uh, economic sections for smallest amount of steel. I mean, in the you can say in the smallest cross-sectional area that you can have, you get the largest and the highest efficiency of the shape. Clear? So hollow sections therefore are quite commonly used and very popular. Another advantage of hollow sections is that you can have them filled with concrete, and then you can achieve what is called as concrete filled tubes, or it is called as encased encased sections. So you can have these hollow sections, and then you can have concrete inside. In fact, you can also add reinforcement to it. So if you look at the section number I, if you refer to section I of AISC 360, it deals with these types of composite sections. Okay. So it deals with two types of composite sections. One is the embedded composite section, other is the encased composite section. So this is what is called as an, I guess this will be called as an encased, yeah, encased composite section. concrete is filled inside this steel periphery. So hollow sections, because of the efficiency that these sections offer, because of their shape, because the local failures are, or they will not happen more, or they are avoided in the hollow sections. Local failures, which I will be talking more about later on, like the local bucklings, local flange buckling, or web bucklings, or the global failures like torsional buckling or lateral torsional buckling. All those types of failures which are a problem in these open sections like I sections, these problems like uh, lateral torsional buckling or torsional buckling or local flange buckling, local web buckling, these types of failures are avoided in hollow section because of its shape. So because of the efficiency of the shape, you are able to avoid a lot of the structural failures which are otherwise seen in open sections like I sections. So efficiency of shape is very important when it comes to hollow sections. Second advantage of using hollow sections is the aesthetic appeal. Aesthetic means it looks good. Hollow sections look neat and clean. Uh, and in many industries, if there is a problem with hygiene, then hollow sections are preferred, because in I sections, what can happen? Dust may deposit over here. For example, if this I section, I'm using it as a beam, dust may get deposited, and there are a lot of open surfaces where there will be problem with rusting, etc. Paint may peel off, so you will see peeled off surfaces over here. So a lot of aesthetic issues also, and therefore hollow sections may be preferred because of their aesthetic appeal. And then third reason is because these hollow sections can be integrated with concrete, and you can have a very high strength composite sections created. So hollow sections find a lot of usage in steel structures. One of the disadvantage of using hollow section, or one of the difficulty of using hollow section, is what? Can anyone just point out a difficulty of using hollow section? Tell me. No one? Advantages, most of us know what are the advantages of using hollow sections, but I'm saying what is one of the dis disadvantage or difficulty in using hollow section. Mr. Nagesh is saying sizes are limited. No, see, so you can always fabricate hollow sections also, just like you can fabricate three plate I sections. You can fabricate hollow sections out of plates. So I would not say sizes are limited. Yeah, the market sizes are of course limited. So if you are buying, let's say from, uh, let's say you are buying a hollow section from Apollo in the Indian market. Apollo and Tata manufacture hollow sections, right? So if you are buying the hollow sections from them, then yes, sizes are limited. But then if you decide to fabricate it on your own, then size, you can fabricate a size of your wish. What Mr. Abdul is saying, yes, internal corrosion. So what was an advantage of hollow section? That it gave you an aesthetic appeal because not many surfaces were visible and the form looks good when you're looking from outside. That also becomes a disadvantage because then you don't understand what is happening inside, right? So if the cancer is spreading inside the body, from outside your body may look healthy, but that cancer is spreading inside your body. Similarly, corrosion and other issues may be eating the hollow section thickness from inside, but from the outside nothing is visible. So yeah, what Mr. Abdul is saying, that internal corrosion is one of the problems in hollow sections. Other problem, as he very rightly pointed out, is the connections. So it becomes difficult to make connections with hollow sections. So two hollow sections, making connections with them is slightly tricky. Especially creating moment connections is very difficult with the use of hollow sections. So this problem gets addressed in section J no, not section J, section K of AISC 360, if you look at it, it addresses this problem of connections with hollow sections, and then there are some connection strategies given for hollow sections. Also, if you refer to AIC 358, there are some prototype connections for hollow sections where you can, of course, they are difficult to execute it on site, difficult to fabricate, and quite complex, I would say. But then there are options available. Options are given in AISC 358 and in this section K of AISC 360. Anyway, so some advantages, some disadvantages, but then these are one of the most preferred sections. And therefore, we will also focus more on these sections. Okay, and this is all known. Very good. So let's now see the historical development of this specification. I'll just bring one notebook. Just wait. Just wait. Yeah. So let us look at the historical development of this specification. And when I say specification, that means the specification for structural steel buildings and what we popularly know as what? Specification. Specification. What is this popularly known as? Specification for, hello, structural steel building. So this is known as the AISC 360 now. Okay. So if I in future, if I use this word specification, this would mean the AISC 360. Clear? So let us look at the historical development of uh, this particular specification. So interestingly, in America, in the USA, what happens that there is no uniform body like the Bureau of Indian Standards. So if you look in the Indian context, there is this Bureau of Indian Standards. Okay. Under this, the Bureau will publish all these standards and not only related to civil engineering, but all across all the design standards, whether they are mechanical standards or electrical standard, whatever, all everything is published by the Bureau of Indian Standards. So you have one central body which publishes all these standards. In the American context, they have different bodies which deal with these, which deals with making the different specification and standards. Clear? So for example, you have the ACI. What is the full form of ACI? So ACI stands for the American Concrete Institute. So it is a, let's say, group of concrete engineers and concrete manufacturers which come together and then they develop their design standards. Is that clear? Similarly, you have, let's say, the ASCE. What is the full form of ASCE? Hello. ASCE full form is American Society of Civil Engineers. Is it? Just check someone. American Society. Can someone check? Of Civil Engineers. So this ASCE, these engineers will come together, form a group, and then under their, you would say under their leadership, the codes get published. Okay. Similarly, you have, let's say, the AISC. What is AISC? What is the full form of AISC? So it is the American, I hope my voice is audible. American Institute for Steel Construction. Is that clear? Am I writing it correctly? Just check. I will also check. American Institute for Steel Construction. American Institute of Steel Construction. Yeah. Okay. Similarly, you have so under this American Institute of Steel Construction, most of the steel uh, related codes are published under their under their guidance or under their leadership. Similarly, you have the ASTM. So what is this ASTM? This is American Society for Materials and something. Just let me see. ASTM. Someone just check quickly and tell me. ASTM full form. ASTM is American. I have just written it somewhere. I'm just not able to get where I have written. ASTM. American Society for Testing and Materials. American Society for Testing and Materials. So all the material related codes, whether it is concrete or whether it is steel or whether it is any other material, all the standards for materials and related to their testing are published by the ASTM. So what I'm trying to say that unlike India where we have a singular body in the form of BIS, Bureau of Indian Standards, which publishes all the standards, you have got different bodies in America, and these different bodies they will publish their own standards, and then these all get ratified by the ANSI. Okay, ratified means approved, or you could say agreed by this one body which is called as ANSI, and it stands for American National Standards Institute. Okay, American National Standards. Therefore, many times you will see the code name as ANSI/AISC. Okay, so therefore many times you will see the code name as ANSI/AISC and maybe let's say 360. So this ANSI will be the nodal body, just like we have Bureau of Indian Standards. It will be this nodal body which will finally be sort of ratifying or agreeing to these standards, and then they get published. Is that clear? Just a basic formation. Hello. Okay. So that's why you see these different names. So any material code, you will see it beginning with ASTM, or any steel design code, you will see it beginning with AISC, or the loading codes usually begin with ASCE, or the concrete codes usually begin with ACI, and so on. So don't get confused with these acronyms. Just keep in mind that these are different institutes or bodies which have the role of publishing different set of standards and codes, and then finally it gets approved by or ratified by this central institute. Okay, let's move ahead. So let us have a look at the historical development of this specification. So this AISC, American Institute of Steel Construction, was set up in the year 1921 with the view of standardizing the steel construction uh, with the view of standardizing the production of steel, the fabrication of steel, the design, to standardize all these things, and even materials. So to standardize all these things, the AISC was set up, American Institute of Steel Construction, in 1921. So I guess it's now what? More than 104 years old. That's a long time. So this institute was set up. Before that, what used to happen, that any steel fabrication company, they used to come up with their different cross sections, they used to come up with their different materials, they used to come up with their different design formulae. This type of thing used to happen. So suppose a manufacturer A, they will make some different section, then there will come a manufacturer B who will be making a different section. Manufacturer B may be using a different steel composition. Manufacturer A may be using a different steel composition. And then these different manufacturer would give their, you could say, design chart. Understood? Design chart means, let's say, the capacity chart which designer can use for their design purposes using these sections. So there was no standardization until then. So to standardize the process of production, design, fabrication, and construction of steel buildings, with this view, AISC was set up in 1921. And then they came up with their first standard in the year 1923. So the first specification for structural steel building came up in the year 1923. So that is more than 102 years old now. Quite old, right? And this first AISC, so it was not named AISC 360 back then. It was just called as the specification for steel building. It was not named as AISC 360. But then this first specification was around 12 to 13 pages only. Very simple, very elegant. I'll just show you that 1923 document also. It is interesting to note what all things were included and how the uh, code was, how the code was designed back then. So the first specification came in 1923, and then came regular revisions. So you can see the revisions over the years. So after 1923 came the revision in 1928, then in 1934, then in 36, then in 41. So these were the war years. World War II was taking place. World War II started in 1939. So these two codes were published or revised during the wartime, Second World War. Then you got a revision in 1949, then in 1961, 69, and so on. So you see regular revisions taking place. And I think since 2000, I think there is a 6 year interval that is usually followed. What I can see, uh, I would say since 1986, they have been following a 6 year revision cycle, isn't it? Somewhere it's 5 years also, but usually it is a 6 year cycle that they have been following. So every 6 years, their code gets revised. So the last revision was in 2016, and the current revision that we are using is the AISC 360 2022. In 1941, as I told you, because wartime was on, the World War II was on. So the 1941 version was released under the War Production Board. So there was a War Production Board because America had ramped up its industrial production by a very large in a very large manner, in a very significant manner after 1941, when they sort of jumped into the World War after the Pearl Harbor strike. They decided to uh, directly get involved in the World War. Before that, the American lawmakers had decided that this world war is not our war, it is war of Europe. We need not get ourselves involved in that. But then after the Pearl Harbor strike on 7th of December 1941, they decided that there is no option now but to jump into the war. And that's when they sort of ramped up their industrial production. And most of the wartime construction, because it was done in steel, most of the, not most, all of the infrastructure that is used in wars, bridges or temporary structures, mostly they are in steel. Your ships are in structural steel, your aeroplanes are in structural steel. So they the overall steel manufacturing and steel usage increased many times during the war years. So the 1941 version was released under the War Production Board, and then there was this national emergency specification for design, fabrication, and erection of structural steel for buildings. Okay, yeah. So this was done. So in 1949, 61, 69, 1941, 49, and 61, these were mainly, you could say, the wartime, although the war ended in 1945, but then you could say the 1949 version was also somewhat a continuation of the 46 version. But then in 1961, in the post-war era, the steel material strengths, this is interesting, just note what I'm saying over here. The steel material strengths in the 1961 version underwent substantial increase. So till that time, the material that was used was around 33 KSI. KSI means kilo pounds per square inch. This is the stress level. Is it clear? Kilo pounds per square inch. Hello, is my voice audible? We would be talking in metric units only, but then from time to time, I may refer to some FPS unit, and I will specify where I am referring to a FPS unit. Okay. So KSI stands for kilo pound per square inch. And how does it uh, convert? So 1 KSI will be around 6 point, I think 6.89 newtons per mm square. Clear? Hello. So 33 KSI will be how many newtons per mm square? Quick. 33 KSI will be how many newtons per mm square? Just multiply 33 into 6.8. So 33 KSI will be to 6.89. Around 230, 227. So 33 KSI will be around 227 newtons per mm square material strength. So this is even slightly weaker than the mild steel grade, isn't it? What is the mild steel strength? When I say mild steel, what is the strength? No one. So mild steel strength is what? 250 newtons per mm square. Mild steel is 250 newtons per mm square Fy. Okay, which comes around 36 KSI. 36 kilopounds per square inch. Anyway, so what I'm trying to tell you that in the 1961 code, you suddenly saw a jump in the material strength. So directly a jump from 33 KSI to 50 KSI. How much will be 50 KSI in newtons per mm square? How much will be the value of 50 KSI in newtons per mm square? So it will be around 345 newtons per mm square, isn't it? So suddenly you saw in this code a jump in the material strength from 227 newtons per mm square to a jump to 345 newtons per mm square. What was the reason? Of course, the reason was advances in metallurgical composition, but nothing much had changed in it. What I'm trying to tell you, that's in most in the steel, 98% is iron anyway. Okay. Whichever steel grade you pick up, almost 98 to 98.5% will be iron. So only the variation is of 2%. Other materials are added, like carbon or uh, silicon or sulfur or phosphorus. So that's just a 2% addition. Otherwise, 98% is iron. But still, why do you get such a large variation in the steel grades? Mostly because of the manufacturing process, mostly because of the quality control, you are able to get different grades. So what happened was that when the 1961 version of steel specification was published, you had the experiences of wartime. Okay, so for 6 years, you had extensively used steel structures under very harsh circumstances in war zones. You had used your steel planes. Steel planes means planes made out of structural steel, ships made out of structural steel, tanks, battle tanks made out of structural steel, houses, bridges, infrastructure made out of structural steel. So you had seen their use in the war, during the war. So, because of their performance in the wartime, World War II, your confidence in the material increased. Understand? So, your confidence in the material increased. Because your confidence in the material increased, you could basically reduce the safety factor. And also during these years, uh, there was substantial improvement in the manufacturing process and quality control. So what I'm trying to say that although nothing much changed in the metallurgical composition, yes, of course, few alloys were added here and there, but remember that 98% is still iron. So although nothing much changed in the metallurgical composition, because of the increased confidence, because of the improved manufacturing processes and quality control, the 1961 version saw a significant jump in the material strength. So as I just repeated, from 33 KSI directly to 50 KSI, you could, you were allowed. Okay. So quite a significant change that came about in the 1961 version. Then in the 1986 version, so up till then, the method that was used was the working stress method. So in the working stress method, you calculated the allowable stress and you limited your section to those stress levels or below those stress levels. So till the 1986 version, it was the working stress based method, or what is called as the allowable stress method. But then in the 1986 version, this ASD method was dropped, allowable stress method was dropped, and then a limit state based approach was introduced, which is called as the LRFD method, load and resistance factor design. So in this case, now because you had a better understanding of the material, you had a better understanding of the section behavior, you had better understanding of the local and global buckling issues. Therefore, because of those better understandings, you could now allow increased strength in these steel sections, and you could check the steel sections for different limit states, and that's how this LRFD method came into existence. So this LRFD method was adopted and the stress based approach was done away with in the 1986 version. So 1986 version is a significant landmark in the journey of the specification for steel buildings, because the 1986 version saw the discontinuation of the allowable stress-based method and an adoption of the LRFD method. Is this clear? So if you recall if I talk in terms of IS 800 also, when IS 800 1984, in the IS 800 1984, it was a stress-based approach. Yes or no? Hello? Anyone who has used the IS 884 version? No one. So if you remember in the 1984 version, there is not much talk about the section classification, or there is not much talk about the uh, limit states of buckling or limit states of torsional buckling, or about the local buckling behavior, local failures. There's not much talk about it in the 84 version. So 84 19 IS 800 1984 version, that is the Indian code, it deals mainly with the stress-based approach, where you find the permissible stress and ensure that it is and ensure that the stress levels in member are maintained below the permissible stress levels. But then when the new code was launched, when the new IS 800 was launched in 2007, you see a shift to the limit state based approach. So similarly in the AISC also this thing happened, that post 1986 or in the 1986 version, they made the shift to the LRFD. And now in the present code, what is happening, that they have included both the LRFD and the allowable strength design. So they don't call it the allowable stress method, they call it the allowable strength design, ASD. Clear? We'll be talking more about it later. Is this much clear? So this is the journey of, you could say, the AISC 360 over the 100 years. I'll be showing you the first AISC of 1923 also. It's it will be interesting to just go through it. But before that, let's also have a look at the historical development of the seismic provisions. So, general understanding the steel industry had was that because steel is inherently ductile as compared to concrete, the steel structures will also be ductile as compared to any RCC structure. So when faced with earthquake, steel structures should not have any significant issues or problems because of their ductile nature. They will be inherently be able to dissipate the earthquake energy, and your overall performance of steel structures will be very good as compared to RCC structures. But then this understanding was challenged by the 1994 earthquake of the which hit the California state. The epicenter was Los Angeles, near Los Angeles, and it is often known as the Northridge earthquake of 1994. So this earthquake came as a root shock to the steel structural community, because till that time, as I just said, it was thought that steel structures will behave quite well under earthquake because they are inherently ductile and nothing should happen to them. But then, after the 94 earthquake, a lot of issues were seen in steel structures also. Lot of local failures in the beam column joints, in the beam column panel zones, near the beam ends, at the column baseplate connections. Lot of failures and lot of signs of distress were seen over here. So that is when the seismic provisions were developed more seriously. Until then, it was just a regular publication. So it was first published in 1992, subsequently revised in 1990. Sorry, it was first published in 1990, subsequently revised in 1992. But as I just said, there was not much seriousness about this particular seismic provision because we thought that steel structures, they will always behave very well under earthquake. But then after the Northridge earthquake of 94, this was challenged because the steel structures did not behave that well. And that is when the next seismic provision, when it came in 1997, considerable changes were made to it. Okay. So after the Northridge earthquake, considerable changes were made to the seismic provision. Structural steel systems were added which could resist the earthquakes in a better manner. And then in the subsequent revisions, all these revisions have been uh, or now include the advancements that have been made in the research and study and understanding of steel structural resistance to seismic loads. So additions till now are 90, 92, 97 is when it underwent a major revision, and then you have got all these revisions. So since 2005, what they did is that since 2005, now the publication has been made consistent with the AISC 360. What that means is that now every time the AISC 360 is revised, automatically you will have the revision made in AISC 341 also. So for example, AISC 360 was revised in 2010. So 341 will also get revised in 2010 and so on. So since 2005, it has been made consistent with the AISC 360. Yeah, that's what I have written over here. So since 2005, the AISC 341 has been made consistent with the AISC 360. AISC 360 serving as the parent code or the primary document. And then in the year 2010, I think a separate code, in the year 2005 itself, a separate code was launched for pre-qualified connections. And we will talk more about pre-qualified connections as we move ahead in the course. So a separate code was launched named as pre-qualified connections, and it was named as AISC 358. And again, its revision has been made consistent with the AISC 360 and AISC 341. So now they have become one family of codes. So AISC 360 will be the parent publication or parent document. Then you will have the seismic provision in AISC 341, and you will have the pre-qualified connections to be used in special moment resisting frames and intermediate moment resisting frames given in AISC 358. So overall, now they become a single family of codes. Clear? Is it clear so far? Any questions, doubts, difficulties you have? Hello. My voice is audible to all of you? Quick. Yes, no, not audible. Okay. All right. So this is what is the a journey through the development of these codes and provisions. Any questions before we move ahead? So now what I will do is that before moving ahead, let's have a look at the first AISC that was published in the year 1923. It will be interesting to just have a look at this particular document. So what I will do, I'll just share my screen and share this PDF on screen with all of you. Are you able to see this PDF? So of course, this is not the original print. This is not the print of 1923. It must have been printed. I mean, this version must have been printed later, but the document is from the 1923 publication. Is that clear? Of course, it did not look like this because this is a typing done on computer. Of course, you didn't have computers back then. But what I mean to say over here is that the contents are same from the 1923 version. I hope this is visible. So this is the first standard specification for steel buildings published by AISC and published in the year 1923, 1st of June. So almost 102 years. Almost 102 years. So as I was telling, I just want you to have a quick look. There are some interesting things that I want to tell. So in 1923, this American institute undertook the work of promoting uniform practice in the industry. So as I was telling you, earlier what used to happen, there was no uniformity amongst the different steel manufacturers, what material they are using, what section sizes they are making, how the designers are doing the design. Nothing was uh, uniform. Uniform means nothing was standardized. Everyone used their own design formula. So it was all jungle. So to standardize all these things, this particular committee was formed, and this committee represented a okay, this is not important. Okay, so interesting to note over here is that in the first committee, there were what? One, two, three, four, five members who were part of this committee, which brought out the first specification in the year 1923. Interesting to note that two people are civil engineers. Okay. Uh, so they are faculty members, it looks like. Professor of Civil Engineering, Harvard University. This fellow is the Dean of College of Engineering and Director of Engineering at the University of Illinois at Urbana-Champaign. So UIUC, what is known as. Uh, this professor is from Harvard. So you have one from the Harvard, one from UIUC. So University of Illinois at Urbana-Champaign is one of the premier civil engineering institutes in America and in the world. Uh, so two civil engineers from faculty, one architect, E.R. Graham is an architect, one practicing engineer, and another practicing engineer. So if you see, very good mix of two practicing engineers, two practicing engineers, two faculty members, okay, and one architect. So it's a great balance that they have been able to strike in this first committee that brought out the first specification that was published back in 1923. I think in the Indian standards, no architects are included in the Codal committee. Correct me if I'm wrong, but till now what I've seen, no architects are usually included in these standards. Yes or no? Anyone could provide more information? What I can recall from the Codal committees that I see, there are no architects involved over there. But if you see over here, in the very first publication, you see an architect, you see two faculty members, and you see two practicing engineers. Unfortunately, in the Indian context, what happens that we do have practicing engineers in our Codal committees. In the Indian context, we do have practicing engineers in the Codal committees, but unfortunately, the code is driven by faculty members, isn't it? Most of the times, the code and the clauses that are included in the code are driven by faculty members, and the research that is carried out by the PhD students or postdoc students of these faculty members. So many times, therefore, as practicing engineers, we feel that the code is not able to represent our aspirations, uh, and many clauses that we get are difficult to comply, mostly because they are not being made by practicing engineers. Practicing engineers are on the committee, are in the committee, but then they don't have enough say. Okay, so in the Indian context, the code is driven mainly by the faculty and their research students. Anyway, so here you see a good balance of two civil engineers, two faculty members, one architect. Very good. Let's move ahead. So very small and brief code. And see, back in the year 1921, 1923, when this was published, and if you look right now, nothing much seems to have changed because the principles of structural engineering remain the same and have remained the same. So I'll share this document. You can go through it. So they are only addressing gentlemen. No, they are not addressing the women because I think back then America was quite racist, sexist, and they did not have any civil engineers, women, I think. So it is addressing only men. So after this, what they are saying. Okay, so just a minute. Are you able to see the screen? I hope you are. Yes. So yes, if it is also there was an interesting line that I had read. So this is a standard specification for design, fabrication, and erection of structural steel buildings, structural steel for buildings. So till now, see, so they are going to focus more on building like structures. So even if you look at the 2022 version of AIC 360, it says that although this AIC 360 may be used for other structures also, it is primarily meant to be used for building like structures. Okay. So here also it says structural steel for buildings. So it present specification contemplates that the inspection is such that improper material is not used or improper material gets duly rejected. It is also understood that the proper loads are taken. So it's not because it's not talking more about loads. It assumes that the structural engineer is well qualified to take proper loads for design and the impact of and the impact is also allowed for each case by adding a proper percentage to the stresses produced by static load. So uh, mostly in case of live loads, what will happen that there might be a possibility of some additional impact due to the dynamic nature of live loads. So it assumes that proper impacts have also been considered. The specification does not attempt to state what the live load, dead loads, or wind load should be. So it's not going to talk about the load calculations because all these factors, it is assuming that the structural engineer is able to carefully calculate. The question of design is all important, and it presupposes or it assumes that the design is good, made by and executed under the supervision of competent structural engineers, and that proper provision is made for secondary stresses, eccentric loads, and unequal distribution of stresses on rivets, etc. So because rivets were the joinery used back then, it's only talking about rivets. And under these conditions, this particular committee, composition of which we just discussed a little while ago, it submits this code for general use on 1st of June 1923. Very interesting. Just a small little 12-page code. So it gets done over here. You see, 12 pages. It starts at page number 7. No, it starts at page number 8 and gets over at page number 16. 9-page code. Very good, isn't it? Hello. Right. Some of the interesting things I would just like to highlight over here, and then we will finish today's session. Another 10-15 minutes, and we will finish today's session. So, but you see, why we are reading this? Because I'm just trying to show you that nothing much has changed over the past 100 years. So to obtain a satisfactory structure, what are the following major requirements? Material should be suitable of uniform quality without defects. You are able to include proper loads. Stresses must be suitable for the material used. So whatever stress levels you are subjecting your material to, it should be capable of taking that stress level. Workmanship should be good. Computations and design must be properly made so that the stresses specified shall not be exceeded, and the structure and its details shall possess the requisite strength and rigidity. Material from where you are supposed to take the material. Structural steel shall conform to standard specification of the American Society for Testing, ASTM. For structural steel for buildings, this is the ASTM A921. This is the material grade that has been specified. Okay. So this was almost, as I just told you, 33 KSI. 33 KSI means around 227 newtons per mm square. 33 KSI would mean 33,000 PSI, 33,000 pounds per square inch. If I want to take it in terms of kilo pounds, I say 33 kilo pounds per square inch, but then I write it as KSI. KSI will stand for kilo pounds per square inch. Okay. So this is the material being used. Loading steel structure shall be designed to sustain the loads imposed, including the weight of steel frame. Uh, Proper provision shall be made for temporary stresses caused by erection. Okay. Live loads, impact and vibration. You will have to add it to static live load. You need to add the impact of live load. Okay. Proper provision shall be made for stresses caused by wind both during erection and after completion of the building. The wind pressure is dependent upon the conditions of exposure, but allowable stresses are based upon steel frame being designed to carry a wind pressure of not less than 20 pounds per square foot during erection and 15 pounds per square foot on the vertical projection of the finished structure. Just calculate this PSF. If someone is there online, just do this calculation. Convert this 15 pounds per square foot into kilonewton per meter square once. Is someone doing it? Just convert. Hello. Just convert. I'll just convert PSF to kilonewton per meter square. I am doing it on the Google. How much it says me? 1 PSF is 0.0478 kilonewton per meter square. So 1 PSF, I just want to see. 1 PSF is 0.0478 478 kilonewtons per meter square. So just convert this and tell me how much will be 15. How much will be 15? So 1 PSF into 15. 0.705. So 0.705 kilonewton per meter square is the wind pressure for which they are expecting that the wind exposure will be less than this particular value, assuming that the pressure, or sorry, the steel frame is designed to carry this much wind pressure, 0.705 kilonewton per meter square. Not much, isn't it? Hello. So suppose in the Indian context, if I was to tell you, maybe a basic wind speed of around 33 meters per second, after applying all those factors, I think it finally will lead to some, or even for a 39 meter per second, not a very tall building, if you have a short building subjected to all those factors, not in the uh, with a normal K2, K1, I think you will get some pressure of similar magnitude, isn't it? 0.705 kilonewton per meter square. Very interesting. Proper provision shall be made to securely fasten the reaction points of all steel. Okay, not a problem. Allowable stresses. So this is where very simple, no complications at all, just simple stress levels which are allowed. So this is like a allowable stress based method. Uh, and all the design actions are presented. How much allowable stress in tension, allowable stress in compression, allowable stress in bending, allowable stress in shear, allowable stress in bearing. And that's what even the codes today do, isn't it? So if you were refer to AISC 360 2022, what they do is from chapter D till chapter G, what they are doing is the allowable strengths. They are just giving you what are the ways to calculate these capacities. So see, it's so easy and so elegantly given over here, isn't it? Hello? Yes or no? Yes. So it starts with these allowable stresses for each action. One by one they have explained. And I'm just seeing at the time. Should I continue or should I stop? 10:07. Uh, okay, have you got any questions? Do you have any questions? Mr. Vineet is asking, these sections from these stresses are conservative? Yeah, so if you see for tension, for example, they are allowing 18,000 psi, pounds per square inch. Okay, so 18,000 psi means 18 ksi, and as I was telling you, the material strength back then was around 33 ksi. Okay, so that means what is the allowable tension level in your cross section? Hello, just do this. What is the allowable tension level? 18 upon 33. So how much? So basically you are allowing around 0.54 Fy, correct? Allowable stress level in your cross section is 0.54 Fy. Yes or no? And if you see now the stress level, so if I were to compare it with, let's say, the stress levels that we allow these days, suppose I were to refer to, let's say, IS 800 1984 version, what is the stress level allowed in tension? What is the stress level allowed in tension? Axial tension. So, anyone? Or even if you refer to, let's say, the section 11 of IS 800 1984, what is the stress level allowed? So, stress level allowed in tension is 0.6 Fy. Hello. Yes or no? The usual level that we allow for tension is 0.6 Fy. So basically, if you compare 100 years ago, we have gone with a 10% increase, isn't it? We have gone ahead with a 10% increase now. Do you understand what I'm trying to say? Yeah. So that is the situation where we are. Got it? So of course, the because of the increase in confidence, now we allow more stress levels as compared to these values. So this is for tension, rolled steel on the net section. That means if there are any holes, bolt holes, sorry, rivet holes, because back then there was uh, holes made for riveting. So on the net section, the stress level shall not be shall not be more than 18 KSI. Mr. Vineet is saying means the section size is now less, of course. So you see a direct 10% reduction in section size in tension, isn't it? Directly you see a 10% section size reduction because earlier you were limiting to 0.54 Fy. In the later codes, you allowed it to 0.6 Fy. Got it? And if you look at the ASD based approach now, which I'll be talking more later, therefore I didn't want to tell you. But if I were to look at the ASD based approach, it will be Fy upon 1.67. Just do an inverse of 1.67. How much? Same, 0.598. Okay. So zero point 0.6 that means. Do you understand what I'm trying to tell? Yeah. So around 10% increase we have allowed over the past 100 years because we have increased confidence in our cross section. Not in the cross section, we have increased confidence in the material behavior. So that's what. See, if you were when was the Empire State Building built? Or forget Empire State Building. It's a RCC structure. No, sorry, it's a Empire State Building. Yeah, it's a RC. It's a masonry plus. It's a steel structure or RC structure. Empire State Building. How could I forget? I just had discussed in the tall buildings course. Anyway, suppose I take the Golden Gate Bridge. So Golden Gate Bridge, an iconic structure, it was built in 19 what 31, 32. When was it built? So if you were to do it today, some people would say, and even I say that what could be achieved in 1931, we are not able to do a proper design 100 years later. Okay. But then if you look at it in other way, what has happened? If you were now to construct this Golden Gate Bridge, probably you could achieve a 15 to 20% less material consumption. You understand? If you were to build the same structure today, design and build it today, probably you could achieve a 15 to 20% less material consumption, not composition, consumption. And the main reason for that is because of the improved manufacturing processes, because of our improved understanding of material behavior, etc., because of our increased confidence, we allow more stresses, we allow more stress levels on our section. Okay. So in tension itself, we are able to see a direct 10% decrease in material consumption if I were to design in tension today as compared to designing a section for tension 100 years ago. Is that clear? Yes. I think we'll stop over here. Today is the first day. So let's stop. And tomorrow we'll just have a quick look at these allowable stresses. We'll just have a quick look at this code. It's interesting to know, go through this code. Therefore, I want us to just have a quick look that the first specification was, how how the first specification was, and then what we will do in the next session is that we will just look at the layout of AISC 360, and then we will go to the standard materials and standard grades that are available as per the AISC 360. So that's what we will do in the next session tomorrow. That's all for today. Thank you. And if you have any questions, you can ask. Otherwise, we end today's session. Yes, please. Okay. So I think we had an interesting first session today. We'll continue from this point tomorrow. Okay. Yeah.